Welcome to lecture number 20 for ECE 461 Control Systems, Root Locus. Now, in the last lecture, we looked at Routh criteria. What Routh criteria tells you is if I have a feedback system, I've got a gain I can adjust. What range of K gives you a stable system? It also tells you whether or not a closed loop system is stable. What it doesn't do is it doesn't tell you if the system behaves well or not. For example, it could have an elevator. If it takes 30 seconds to get to the next level, that's stable. Not useful, but stable. If an elevator that took the patrons and bounced them up and down like this, and eventually settles out, that's also stable. Again, not useful, but stable. So if I want to find out what is the best gain, Routh tables, Routh criteria don't tell you that. I need a different tool. And that tool is Root Locus. Now, as an example, let's take the following system. If I have a third order system, this type 1, I've got the open loop system G of S, close the feedback loop, I get GK over 1 plus GK. What value of K is best? And you can sit there and try that. This is where programs like Vism are useful. This gain up here is K. I can sit there and see what happens as I vary K. If K is really, really small, I get a system with no overshoot, looks like about a single dominant pole that's very slow. Increase the gain, I get a faster system. That means the real pole's moving along the x-axis, the real axis. Now I'm starting to get overshoot. That means my pole's starting to become complex. It's getting faster and faster with more and more overshoot. As I keep on cranking up the gain, eventually I hit the j omega axis. Routh criteria says K's got to be less than 2.5. That's this point. That's where I'm on the j omega axis. And more than 0. You can get a lot of different responses between 0 and 2.5. If I want a certain overshoot, like 25% overshoot, that's where I want the gain. I want the gain to be 0.45. So I need a way to look at how the poles shift as I adjust the gain. That's what Root Locus is. Once I know how the poles shift, I can sit there and find out what is the best gain, which really means make the gain as large as possible, but not so large I have too much overshoot. So again, that's what Root Locus does. It takes a feedback system like this and says, if K can vary between 0 and infinity, what are the roots of the closed loop system? Or what are the locus of the roots? Hence the name Root Locus. Once I know the roots, the Root Locus plot, that's my shopping list. I can get any response that's on the Root Locus. The best gain is then the gain that gives you, or the highest gain, because high gains give you fast systems, small error, but doesn't give you too much overshoot. A couple definitions before we start. The open loop gain, again we're assuming a unity feedback system like this. The open loop gain is just GK. Take out the feedback loop and that's the gain of the system. The closed loop gain becomes the gain from U to Y, GK over 1 plus the loop gain, GK over 1 plus GK. The open loop poles are the poles of GK. Open loop zeros are the zeros of GK. The closed loop poles, when you close the feedback loop, the poles shift. And it turns out the closed loop poles are the open loop poles plus K times the open loop zeros. The roots to that polynomial are the roots to the closed loop system. And that's what we really care about, is the closed loop system stable. And the Root Locus is just a plot of the roots, the locus of the roots of the closed loop system as K goes from 0 to infinity. Now, to plot a Root Locus plot, there's a couple of different approaches. The approach that Matlab uses is brute force. It's pick 1,000 values of K, or some large number of K, calculate the roots of GK over 1 plus GK for each of those Ks, and then plot. Real versus complex. This is numerically really bad way to do it, but with Matlab does numerical methods really, really well, so it actually does make sense. For example, if I have the following polynomial, I want to find out what are the roots of this polynomial as K goes from 0 to infinity. In Matlab, what I would do is first input the polynomial. This gives me 1, 25, 100, 0. That's s to the fourth plus 25s cubed plus 100s plus 0. Have z in the same dimensions. The numerator, that 1000, is 0s squared plus 0s cubed plus 0s squared plus 0s plus 1,000. Now we can add the two together. P plus k times z, find the roots of that polynomial, and then when I'm done, put a star at each point. And this is what I get. And notice that I start out with a pole at s equals 0. That's what I had in the simulation when the gain is really small. Increase the gain, the pole moves left. That's what we're seeing right here. When the gain is really, really small, not that small, really, really small, I get a pole that's real and slow. Increase it, I'm moving along the real axis, going left. If I keep on cranking up the gain, eventually start getting complex poles. And again, that's what's happening here. Crank up the gain. I'm starting to get overshoot. That means my pole just became complex. Increase the gain even further. I start to get more and more overshoot, that eventually becomes an oscillator. And again, that's what we're seeing when you simulate it. Increase the gain, I start getting more and more overshoot. It's moving along the root locus plot. And eventually at 2.5, it's an oscillator. So this describes how the system behaves. This is the root locus plot. And kind of the oddity, this point right here, this is equal spacing in k. Well, log spacing, actually equal spacing in k. Right at this point, if k varies just a little bit, the poles shift a lot. We're going to be using that feature a little bit later. That's to calculate the breakaway point, this point right here. The sensitivity becomes infinity. Stay tuned to next lecture, and we'll come back to that. Second way to plot the root locus is the Matlab command rlocus. It's really the same thing as method number 1, but a little bit more elegant. I just pick my gains k, I have my system g, and say, what is the root locus of g and k? And what you get is a plot like this. Same thing, it puts an x where the poles are. These poles come together, split apart, and become complex. Third approach is graphical. Now the problem with the previous two approaches, they do work, but they don't give you a lot of insight as to what's happening. And that'll be important later. Later on we're going to say, instead of having k just being a gain, suppose I could add dynamics in there. I could add zeros and poles. Where do you want to put those zeros and poles? How do you want to warp the root locus plot? Again, the previous two methods don't really give you insight as to how the root locus plot behaves or why it behaves that way. This approach does, which is why we're going to go over the graphical method. The procedure is to first assume a unity feedback system like so, and then g times k I'll define as k, just a gain, times zeros over poles. The numerator called the zeros, denominator is called the poles, and that's because if I plot the gain versus frequency, when the numerator is equal to 0, the gain is 0, hence the name 0. When the denominator is equal to 0, I divide by 0, and the gain goes to infinity. So it's like you took a membrane and stretch it to infinity with a pole underneath the membrane, hence the word pole. Regardless, I've got two polynomials, zeros and poles. The closed loop gain is gk over 1 plus gk. Do a little bit of algebra. The denominator becomes p of s plus k times z of s. So really what I want to do when I sketch the root locus, what are the roots to p of s, the open loop poles, plus k times z of s, the open loop zeros? Those roots are the closed loop poles. Now, in order to find the roots, there's a couple ways to do it. If I rewrite that p of s plus k times z of s equals 0, bring the k right, divide through by z, and I get p of s over z of s is minus k, which actually has two conditions. The amplitude is k, the angle is 180 degrees. The amplitude is how we're going to find k. Pick a point on the root locus, plug in s, and p of s over z of s is k, or cross multiplying. K times z, or k times g is 1. For the root locus, the angle is what's important. This says that any point on the s-plane where p of s over z of s equals 180 degrees is a point on the root locus. And it turns out that p of s, a graphical way to interpret that, is the angle from the poles to s minus the angle from the zeros to s. If those angles add to 180 degrees, that's a point on the root locus. So let's do a couple examples. the rules to draw the root locus plot. I'll give an example. Here's a third order system, poles at 0, -5, and -20. Now let's draw the root locus. The root locus are the solutions to P of S plus K times Z of S equals 0. That's the poles, there are none, plus correction poles, 0, -5, -20, plus K times 1000 equals 0. Now note, when K equals 0, the roots are the open loop poles. So put an X at those three spots, 0, -5, -20. The zeros, as K goes to infinity, the roots go to the zeros. In this case, there aren't any zeros, so I don't mark that. If I did have a 0, I'd put a 0 there. Next, let's draw the real axis loci. The root locus is any point where the angles from the poles to your point add up to 180 degrees. If I pick a point over here, angle from this pole is 0, the angle from this pole is 0, angle from that pole is 0, 0 plus 0 plus 0 is 0. This isn't on the root locus. Over here, I've got 180 degrees, angle from this pole, plus 0 is 180, that works. Over here, I've got 180 plus 180 is 0. It doesn't work. Over here, I've got 180 plus 180 plus 180. Basically, it's an even odd. If there's an odd number of poles and zeros to the right, that's part of the real axis loci. There's a solution to this polynomial in this region. An even number is not on the root locus. So the real axis loci are between 0 and -5, -20, and -infinity. Asymptotes. Poles go to the zeros. This pole goes to -infinity. These two poles come together, and they got to go somewhere. There aren't any zeros for it to go to, so these two poles have to go to an asymptote. And that's what these red lines are. To figure out what the asymptotes are, I need the number of asymptotes. I've got 3 extra poles. The 3 poles, no zeros. 3 extra poles have to go somewhere. They go to your three asymptotes. The asymptote angle is 3 times theta is 180 degrees. Solve for theta. It turns out you get plus 60, minus 60, and 180. 180 is an oddity. 3 times 180 is 180. That's because 180 once, 180 twice, 180 3 times, and back at 180. That's the asymptote angle. The asymptote intersect is the center of mass. Treat poles as 1 kilogram, treat zeros as -1 kilogram. Where's the center of mass? And here the average of 0, -5, -20 is -25 over 3, -8.33. So there's the asymptote intersect. Next, I want the breakaway point. These two poles come together, split apart, and then go to the asymptote. The breakaway point is where they split away from the real axis. There's a couple ways to do that. One approach is think of this as minus charges and place an electron where the electron's in equilibrium is the breakaway point. And if this extra pole at -20 wasn't there, by symmetry it'd be right in the middle. Poles repel, poles act as minus charges, so it's going to push the breakaway point to the right just a little bit. So that's going to be like -2.11. Second way to calculate it, that's the point where the sensitivity is infinity. So the derivative of 1 over g, p of s over z of s equals 0, or the derivative of g of s equals infinity. Find that point, and turns out the solution is -2.11. Or a third approach, this is kind of what I actually do. On your calculator, just do a search. Search along the line x plus j.01. Where do the angles add up to 180 degrees? As soon as I find it, that's the breakaway point. So one of those ways does it. On the tests, I would just estimate it. It's between 0 and -5. Say it's -2.5, pushed right, about -2.2. Actually -2.11. The j omega crossing. Now I know that I split apart at the breakaway point and go to the asymptote. To help sketch the root locus, it's nice to know what the j omega crossing is. There is no closed form solution for this. You just have to guess again, guess again. What I do is I plug in s equals j omega for g of s and find out where do the angles add up to 180 degrees. Turns out they add up at j10, so that's your j omega crossing. And part of the reason there's no closed form solution, the angle is actually angle from the poles to your point on the root locus. I get 90 degrees plus the arctangent of x over 5 plus the arctangent of x over 20 equals 180. Solve for x. Arctangent is a nasty nonlinear function. It doesn't simplify. You really have to use numerical methods to find it. If you have complex poles and zeros, the departure angle is whatever it takes to make the angles add up. We'll talk about that in our next lecture. But those are the rules for drawing the root locus. Once you get the root locus plot, define the gain at any point, like if I want to put the closed loop pole right here. At any point in the root locus, g times k is minus 1. The minus is the 180 degrees. That tells you you're on the root locus. And the 1 is the amplitude. The value of k, that makes the gain 1 here, puts you at minus 2 plus j5. So those are the rules. Again, those in lecture notes. We won't spend much time on that. Let's go through 3 examples. Suppose my plant is 1 over s plus 2. In that case, I've got a pole at 0 and minus 2. Real axis loci in the middle, that's when I have even odd. Here's the even number of poles to the right, 0, 1, 2. Here's the real axis loci. The breakaway point by symmetry is right in the middle, minus 1. The asymptote angle is 90 degrees. I have 2 extra poles. 2 times theta is 180. Solve for theta. Theta is plus minus 90 degrees. And the asymptote intersect is the center mass, minus 1. So these 2 poles come together, split apart, go straight up and down. Now what that tells you is that when k is small, I've got a real pole. As k increases, the pole moves left, and I get a faster and faster system. Still real, still no overshoot. Then I start getting overshoot. When I get overshoot, the settling time stays constant. The real part's constant. Settling time is always 4 over 1, 4 seconds. But the overshoot gets bigger and bigger. Second example. Suppose I have 3 poles. I've got a pole at 0, minus 2, minus 5. So put an x at those 3 spots. Real axis loci. It goes to even odd. So here is 0, 1, 2, 3. The real axis loci are between 0 and minus 2, minus 5, minus infinity. Asymptotes. I've got 3 extra poles. I've got 3 asymptotes. The center mass is the average of 0, minus 2, minus 5, minus 7/3. Going up at 60 degrees, minus 60 and 180. The breakaway point is the midpoint pushed right by that second pole, or that third pole, puts you at right around minus 1.8, or minus 0.8. And finally, the J mega crossing. These 2 poles come together, split apart, get pushed away by that third pole, and pole acts minus charges, repels the root locus, and the J mega crossing is right here at 3.16. Last example, if I have 4 poles, again for even odd, I've got even, odd, even, odd, even. Real axis loci are between 0 and minus 2, minus 4 and minus 5. I've got 4 asymptotes, split up the plane symmetrically 4 ways. 4 times theta is 180, so theta is 45 degrees. 4 times 45 is 180. 135 degrees. 4 times 135 is 180. It actually spins around once, and the one's back at 180. Plus the complex conjugates, minus 45, minus 135 degrees. The asymptote intersect is the center of mass. The average of the poles is right here at minus 2.75. The breakaway point, I actually have 2 of them. It's the midpoint pushed right for this one, midpoint pushed left for the second one. And the J mega crossing, if you calculate it, the point on the J mega axis where the angles add up is at J 1.90. So that's sketching a root locus plot. And the following lectures will be using root locus plots to calculate feedback gains. But that's lecture number 20 for ECE 461, root locus.